Très bien. Bienvenue au séminaire d'Intuit. On a le plaisir d'accueillir Eduardo Martini, brésilien qui a fait sa thèse à Poitiers, l'Institut Pépin.
Oui, au Brésil.
Pardon?
La thèse, j'ai fait ITA au Brésil.
Au Brésil.
J'ai fait le postdoc.
Ah, pardon. Donc avec, il vous disait, Peter Jordan. Et aujourd'hui, tu es maître de conférence, pris enseignement présentiellement. Et donc, tu vas nous présenter ton travail sur le contrôle, modélisation. Merci.
Merci à vous. Déjà, c'est le présenter en anglais?
Tu fais comme tu veux.
Okay, that's gonna be slightly.
La plupart des gens en ligne comprennent le français, donc mais tu peux le faire en anglais.
Oh, je fais en anglais.
Okay.
So both
You can.
Okay, so thank you all for coming. I wasn't expecting that many people. Okay, I'm presenting a bunch of linear tools for control and modeling that I have developed. In particular, we're going to talk about the previous study that was already published about flow control. I'm going to revisit what I think are some advantages of the method, some nice features of the approach. And on modeling is something I'm working right now. We're gonna get there. So those are the main actors involved in this project. So myself, with Peter, Aaron, and Andrea, we have worked together on the flow control approach. Tim Colonius is collaborating on the second part of the modeling. So it's two different works. So a small outline. This is more from my own organization, but much of slides about flow estimation and control. We're going to talk about the theory. We are redeveloping optimal control using not the most standard way, and then we have some experimental applications where we need control and test waves and jets, and then the full modeling approach where we want to essentially break down long-range interactions in something we can interpret physically in a slightly easier way. So this is I don't think you need to justify why flow control is interesting, but just for completeness, here's just one illustration of flow estimation. Just to say that estimation can be useful in flows, even using a linear method, as everything I'm presenting here. We are based on the linear framework. But even a linear estimation of a non-linear flow can give us some nice results, which points toward the fact that we can use linear control methods to control complex flows. So this is just another example we did experimentally. On blue here is a hot wire measurement on the center line of a turbulent jet. And the red lines are just real-time estimations of this flow. Again, using the approach I'm gonna detail soon, but again, the point is that we have a pretty good match, which again points towards the fact that we can use control to try to get something out of this flow. Application for control, I think the holy grail is transition delay. If we manage transition avoidance, it's often a bit optimistic, but in some cases that can be done. So Moher et al. Showed a case where they, just by counteracting incoming waves, they could postpone the formation of transition waves and thus the onset of transition. And this is a work by Leclerc et al., which I find very cool. Something I wanted to do a long time ago, I never did first. Kudos to him. Where he basically started with a turbulent channel flow. So this is just the PSD. The turbulent flow has many harmonics, not super turbulent, but turbulent. And what he did was to develop a linear control based on the mean flow. At this state, you get optimal control in this position. He applies the optimal control. As we expect, we don't really linearize the flow because at some point the base flow changed enough that the linear control is not effective anymore. So the idea here was to develop a new control to try to further reduce all the perturbations, and then you can see that it's basically killing the higher harmonics, and it keeps iterating on that. At some point, they managed to get a control that pushed him all the way to the linear state, starting from a fully turbulent state. Many questions open, how we can do that in a somewhat automatic way. I mean, here, if I remember correctly, it was a simulation, so you can stop, you can rebuild all your controls, how you do that. So that is applicable to more general cases. I think it's still not in question, but then anyway. So when we talk about control, we have to choose what the control strategies we want to use, and there's just too many flavors of them. I'm briefly going to mention a few. Sasaki was a colleague of mine at ITER. He worked a lot with wave cancellation approach, which is very suiting for any undergrad student because you have an incoming wave, you put a minus wave, and you cancel it out. So it's as simple as you can imagine. But he got very nice results on that. It's quite inexpensive to use, and feature I like the most is this physical interpretation. On top of optimality of controls, really understanding what's going on, it's something that I like. And then you can move on top of that. So, okay, this is just physics inspired. We can use control theory to find the optimal control. The optimal control here is, of course, using the electron, so minimizing the perturbation energy, which is great because now we have formally the optimal, at least within the assumptions of a linear system, but only at the design point. If we apply the flow on a slightly different Reynolds numbers, slightly different incoming velocity, or any other perturbation, we are away from optimality, and often you can introduce instabilities instead of controlling the flow. To remediate that, there is robust control theory, where we say, okay, I don't want to, I'm moving away from the optimal control. I want something that works on a huge parametric space. So I can change velocity. It's not going to be as good as that one, but it will never be as bad as that one when I change the input velocities, which is also always going to be the case if you're putting that in some sort of practical use. Adaptive control is something I found fascinating, and I never got the chance to play with, but I think it's relevant to mention here. In my opinion, it kind of merges those two, the qualities of those two. So we keep updating the control law with a given formula, with a given expression, but that can account for changes in the flow in real time. The only problem is that here you need to have a measurement on your target all the time to update your control law. So if you can do it, it's great. If you want to reduce jet perturbations, as we're going to show, it's hard to have a sensor downstream of the jet to adapt your control in real time. And then we have nonlinear control, which is challenging. We're talking about nonlinear systems. As far as I know, there's no unified theory of nonlinear control. If someone should use it. It's tough. And you can pick your flavors. There's probably 100 other strategies for control. For what concerns this talk, we're going to talk about nonlinear control. So typically what we're going to start is from a nonlinear equation. Here is just a generic representation of the Navier-Stokes equations. This is the Navier-Stokes operator, and we're going to force this with an external force. So F here just means any external perturbation that we have no control of. It could be the incoming turbulence, it could be anything else. A is some sort of actuation, so that's what we're going to put into our equations to modify the flow. And define a set of sensors. So Y here, it's a sensor, can measure velocity, pressure, stress, or whatever you want, which is in general a nonlinear function of the state. And likewise, we have the target, so that's what we want to minimize. The trivial stuff we might want to minimize is just identity operator here, which minimizes the perturbations on the whole flow, but we can be more restricted than that. If you assume that the perturbations are small, we can linearize all of the system, we get back to classical linear framework for the flow. Where F here, yes, it represents the external forces, but as it has been tradition for the last 10 or almost 15 years. We can also think this thing as modeling all of the nonlinear terms if we are neglecting to remain this. Strictly speaking, if you do that, there should be no nonlinear terms because we are making an infinitesimal perturbation. But often we just do that on the mean flow, which is not a fixed point of the solution, and we just throw all the non-linearities in an unknown math and hope for the best. Basically, the approach. The problems with classical control method is that well, we have to get your system, a linear system. To get your optimal control, your optimal estimation, we have to solve an equation of this type, the algebraic Ricard equation. Any numerical tool has this thing built in. The problem is that the cost of that grows very fast, 10 to the cube. So basically, what you need to do to apply classical tools is to get a reduced order model for A with 1,000 degrees of freedom, maybe slightly more, so that this thing is feasible. And then, so it's a strategy that's called the reduce then design. You reduce a controller on the, you design the controller on a reducer of the model, and you apply for the full system, and you hope for the best. There's more formalism than that, but we're not going to delve into that. And to reduce the system, many strategies based on PID modes, POD modes, balancing modes. This is not really a reducer of the method, but you can kind of get the same results using iterative methods to solve directly for the control gains. The drawbacks, which I personally don't like, and some people don't mind that much, is that there are many choices to use reducer order models. Typically, balanced modes are the most robust, but you have to do that. So often constructing the reducer order model is as expensive or more expensive than doing the control model in the first place. And most of the methods that use the classical control framework assume that the external perturbations, the F I showed before, is modeled as a white noise. Sometimes with spatial correlations. It is possible to put some time correlations in that, but I've never seen anyone doing that because the whole thing just gets trouble. So I just want to talk a bit about the wave cancellation strategy, just because it kind of gives the basis of the control method I'll present next, at least in a pictorial form. So the idea is that you have some sort of perturbation. Here I just changed the notation, I don't know why. So now some sort of wave is created by external perturbation D, again, in flow conditions of perturbations, and this travels downstream. So the idea is that we want to build some actuations. We're going to read this wave at this point, and you're going to act on it further downstream, hoping that we add the wave with the red wave, and the resulting wave we just cancel everything that is to the right. It's as simple as that, and this simple picture is basically what Sasaki used in 2018 to do some control, because the whole point was that we can model all of these waves using a parabolized stability equations to track single waves traveling to the domain in a very inexpensive way. So you could estimate this wave, you could get what's the transfer function that an actuation halfway through would give to the flow, and build the controller based on that. So that's his setup. He has like a perturbation upstream, a sensor. Here he uses a different method. That's the activation and the target. And all of these transfer functions he computed using PSC. So he did the whole thing in a notebook. It's very inexpensive. And from there, he could get the transfer function between the actuation and the target, how everything he was reading in the sensor was related to the target. And the underlying assumption is that everything that happens at Z is a linear combination. And here I'm in frequency domain, but roughly the idea is that everything that happens there, we can write as a linear combination of everything that is passing through our sensor, plus a linear combination of our actuation there. If that's the case, sorry, I just messed up. So here should be D. Everything that happens in Z is a linear combination of the perturbation and my actuation. And here it's completely screwed up, should be this equation. We're going to estimate what's going there. Since I don't have access to D, is whatever is incoming, I'm going to do my best to say that everything is in Z. I can write the linear combination of what I'm reading and how I'm acting on the flow. I'm going to make a restriction that all my actuations should be a linear function in terms of my readings. The only information I have on the flow is what I'm reading in the flow. And then I can rewrite everything that is happening in there as a linear combination of what I'm reading, my actuation, which I can write in terms of what I read. So if I choose this gamma here, there's a minus sign here, as just the ratio of those two guys, I can basically cancel everything which is in the parentheses. So hopefully what I get there is 0, which is that's never the case because this doesn't model the whole problem. But it's this simple reasoning that led to the wave cancellation approach. And those are basically the results. So the framework used to do that was a mixing layer. So we have a shear layer here, I'm plotting vorticity. At some point we get the Kelvin stability triggered, we have vortex formation, there's vortex pairing downstream. We started by estimating a position downstream. I forgot to write down what was the position, but if I remember correctly, it's around x equals 300. And he has a small transient here, but after a while, like the estimation and the DNS put on top of each other. Based on that, he designed the control. Again, just using a linear estimation. That's what he got on the right. So again, there's a bunch of transients there. The whole point is that the blue line was the uncontrolled simulation using the same perturbation, the same initial conditions. For the controlled flow, he gets this black line. So we got a reduction of roughly 2/3 of the perturbations at our target. So that was quite interesting. Open questions after he did his work is that what are the perturbations we can control? So that's a somewhat simpler case. It's a mixing layer. We know that everything is going to be a Kelvin Helmholtz after a while, at least in the regime. In a more general case, if we have many waves, how we track that? Can we do better? So this was just based on the feeling approach. How free are we in terms of actuator and sensors? So we just chose something. This is a convective system, so we know that waves are going from the left to the right. So in his approach, you need to have the sensors on the left of the actuator. Is that an absolute necessity? Can we do things better? From his approach, it's not clear. And it would be nice to have a formal formalism to add some robustness, to add some formalization to the process. So to do that, what we did is to move everything to the frequency domain. This is the same equations as before. Everything should have heads here, but basically the time derivative becomes I omega, standard Fourier transform. And the idea of the system is that we can, since everything here becomes algebraic, we can write our equation, we can write our sensor readings and our targets directly in terms of the resolvent operator, which is just the inverse of this guy, and our observation matrices. So basically inverting this equation, U equals RF plus A. Here I'm ignoring A for the first moment. So this gives me a pretty simple, straightforward direction. And that leads us to the concept of observable forces. What is an observable force? It's something that perturbs the flow in such a way that I can measure it with my sensor. So if I put a force in here that projects at the null space of this operator, I have 0 readings on my sensor, where if I cannot measure something, there's no hope I'm going to control it, right? That's basically our understanding of that. Likewise, on the Z, if a forcing doesn't create a reading on our targets, we don't care about forcing, we don't want to control something that doesn't affect our objective. So it's really like the subspace that the forces that can be observed and that create a reading on the target that is really our interest. If you want to formalize that using a pseudo inverse. So if y equals this operator times f, we call the observable f the pseudo inverse applied to y. So it's roughly the adjoint, the sensitivity. How are my sensor y sensitive to external forces? That's what this object gives us. And we studied that in our first study was on a boundary layer. So here, it's just a boundary layer, was Reynolds 1000 based on the initial displacement thickness. All the green circles were sensors I used. So were just control positions. The diamonds here were sensors I used, and we try to understand what are the forces that each sensor constructs. So starting from here, let's see from the previous slide, the observable force is just the adjoint applied to the sensor. So we just did that. We just applied the adjoint resultant forced by this guy. We got a mode like that. So that's everyone recognizes that as a Stomich Richtling / initialized by a R mechanism wave, meaning that the forces that create readings here have this time. So this is the type of external perturbation I can measure, or at least I can only measure stuff that has a non-move projection at this point. If you do the same thing for the other point, we have a similar wave from here all the way to the left. What you find out is that it gives more information if you make the orthogonal basis on that. So pretty much remove everything that was here. So we can interpret this thing of all the extra forces we can capture with this sensor that we could not capture with the previous sensor. Okay, we measured we define here what are the forces we can control on the flow, but we don't want to control forces, we want to control some perturbations, the result of those forces. So what we did is just compute the response of the whole flow to this forcing, and we got this type of waves. Those are too similar because this is a fairly low rank system. It's on the layer, everything is going to look like Stomich Richtling if the domain is big enough. But you can see that this forcing has like larger amplitudes slightly upstream. This forcing only kicks off more downstream. Makes sense because the forces are downstream.
Sorry, which components are you showing?
Sorry, good question. This was all stream-wide components. Okay. So this was the whole idea. This was the whole thing that kick-started my journey into control. My gut feeling, which I had no proof at the time, was that, look, if I can only observe those forces, this is the only thing I can control. So whatever I do in terms of optimal control, we can only do that because anything else cannot be controlled for. I just threw that in the air, and it took me a year or so to formalize. Those things are, for those, many of you are probably well versed in control theory. This has direct relation to controllability modes, of course. We're not being anything new. Personally, I like this kind of interpretation because I did this for one particular frequency. You can do that for all the frequencies. The controllability modes are a linear combination, weighted linear combination of the responses on all the frequencies. But I find the controllability modes less interpretable. This in the frequency domain is easy to understand what the physical easier to understand what are the physical mechanisms of each type of on each frequency, and particularly if you want to tackle one specific frequency, there's a resonance, there's something else. We can look directly what are the observable forces, what are the responses, and try to understand what's going on. So then the question was how we formalize this thing for estimation and control. So this is basically redoing linear control here. We start with non-causal control. That means we estimate non-causal estimation. We estimate everything a posteriori. That was our first approach to the problem. So the goal is to have a flow U. We want to find a U tilde that minimizes the. It's the same kind of of Lagrangian you want to minimize in a standard common filter. We put the restriction that U tilde needs to be a linear combination of our sensors. And we also consider that we have some sort of sensor noise, and we consider that all the external perturbations have correlations, right? So this is a generic forcing CSD, so the correlation of the external disturbances. We can solve this thing directly in the frequency domain, which gives us an expression for this TU, which goes like that. So it gives the matrix equation that gives me the optimal transfer function between sensors and estimated flow. Some features of that is that, well, it only depends on the resonant operator. So we need to be able to compute that. We're going to talk about that soon, but there are ways we can do that quite nicely. The other nice feature is that, again, it's a simple matrix equation, but the forcing CSD appears here. So if you have a model for the color of your forcing, for the spatial temporal distribution of forcing, you just have to plug this thing here into the matrix, and it's automatically taken care of. This whole thing is solved in the frequency domain here, but the idea is that we solve this thing in the frequency domain, we move back to our time domain, and you get a convolution we have to do with our sensors to estimate the flow. So here's an example we did on this type of estimation. We explored this in a follow-up study. So up to now, we were talking about a paper I did in 2020, developing the optimal estimation using this frequency domain approach. And here, Amaral did a follow-up study, seeing okay, what that really represents on the flow, how good or bad can we do that. And I could highlight here on the role of using proper forcing CST. So this is a channel flow. Okay, we are estimating the streamwise component using only shear sensors on the wall. On the top panel here, we have well, 3 different positions. So Y plus at 15, 100, and 200, so moving away from the wall. On the bottom, we have an estimation using F equals to I. That means you assume that the whole thing is just white noise and not adding any physical information on the flow. And you know, if you're close enough to the wall where the sensors are, this is pretty good. As soon as you move away, we have a completely crash of estimation. No estimating everything. But if you put F, and here we cheated a bit, of course. We computed the nonlinear terms directly from the numerical simulation, from the DNS, and we computed all the statistics of the nonlinear terms, and we used those terms to construct F. But I don't have any real-time information on the nonlinear terms, only the statistics. If I use that in my estimation, well, now what I get is this. Of course, I lose fidelity when I move away from the wall, but this is a clear improvement compared to more simple forcing terms. And if everything works, I have a video of that. Let's see if it's there. So it's quite nice. Here we have one extra information where instead of doing that, we're using an analytic viscosity model. We don't have to dwell into when or when not use viscosity models for linear systems, but just to say that this here is the improvement on top of a white noise approach where we don't assume anything, but we can do better. Right? This is quite close to the DNS results. So okay, so that points us to the direction that we have an estimation framework that is nice. So we got something new, which was we have an easy way to incorporate all of the turbulent statistics if we have them. I don't show this here, but we develop some methods to retain a low rate estimation of that based on a few sensors in case you don't have a full DNS to work with. So we can get like approximate that without having to do the full numerical simulation prior to estimation. Okay. Now we get to the point how we do that for large systems. because so far we did that on a channel flow. So we get Fourier in time, Fourier in alpha, in x, Fourier in z. We end up with a matrix of 100 degrees of freedom, or the whole resolvent that joins pseudo inverse is straightforward to do. The question is, can we push that to more complex flows? And that's what gets us to time integration methods. So what I need to compute what we need to compute the whole control is to construct those terms. And here, for simplification, I'm assuming f equals I. The only thing I need is the resolvent operator, and here is a shorthand notation for the resolvent between a force in F and the output Y. So we need to add the D matrix on the right and the C matrix on the left. And it's a joint. So what you see that the only thing we really need is the composition of those two terms in my equation. And how we do that for large systems. So the goal is to do, we start the system with an adjoint run. So we just solve the adjoint system, forcing the system at my sensor with a delta in time. In practice, we do initial conditions to emulate that, but that's details. The point is that if you Fourier transform the solution of that, what you get in the frequency domain is directly R dagger Cy. So we basically already have this term. And again, just to show what this looks like, this is for one sensor located here. We just have like the sensitivity of the mode that moves to the left, that gives us a frequency domain representation of all of the observable forces we have in this row. I forgot to mention this. We call this in English. March descendant, backward facing step, which of course have all the sensitivities on the left. But we need the product of this guy by the knotted joint. So what we do is that we use the solution of this equation to force a direct equation. And again, if you transform this thing to the frequency domain, what you get is the solution of the field is R. We have the BF, which is going to filter out all the sensitivities to the place where we actually have external disturbances, or where we're modeling the external disturbances are. And from here, we can construct this product. So if you on the left, we have a time domain representation of the observable forces. This would be a representation of the controllable perturbations. That is, it's just the response of the forces we have on the left. The backward facing step flow. So here we have a shear layer. We have Kelvin-Helmholtz like waves which get amplified downstream. So nice thing is that we have to do that for each sensor. So in this case, what I'm going to do, I have 3 sensors. I have to repeat this procedure for 3 sensors. But after that, I have all the information I need to construct any sort of estimation and distributed alpha of control. So it's fairly inexpensive. In my opinion, it's about the same cost we need with time steppers to construct some sort of reducer of the models. But you already got all the information to the control. The question is now, with that approach, we could redo everything we did for the channel. But the point is now want to move forward and use that for real-time applications. And the goal here is just to add a constraint in my equation using Laplace multipliers to enforce causality. So I want to optimize this with the constraints that all my transfer functions are 0 for negative times. I'm going over time already. You have okay. Time. I try not to spend too much time. So basically, I get the same equation I had before in the frequency domain with this guy. This is a classical Wiener-Hopf problem. I'm going to talk about details. We found a very nice method to do that. We can only work with that analytically if you have 1 degree of freedom. If you want to use multiple sensors, it's messy because Wiener-Hopf problems don't have analytical solutions. But we find a numerical method that works quite well. We do that on a notebook, so it's just not expensive at all, with multiple sensors, multiple actuators. And the extension of this estimation, causal estimation, to a causal control, it's quite straightforward. We just minimize the perturbations. We add here a penalization on the actuation, so that's the actuation penalization term. The formalism to enforce causality is the same. We get a slightly different equation, but it's the underlying idea is the same. So how that works? We did some tests on the backward fixing step. The idea is that all my perturbations are located here on this square. I want to control them first moment using this sensor with this actuator to reduce perturbations on this target. And then we wanted to compare what the causal control kernel, that is what we can use in real time, and with a non-causal control, which is not applicable at all, but it's the optimal. It's a nice benchmark what we could do if you knew the future, right? And then we're going to truncate this non-causal control to its causal part. Just what I'm going to show now is quite abrupt. That's essentially what we did for the wave canceling approach. So here I'm just showing the control kernel, that is what I'm convoluting with my sensor to get our optimal control in the triangle there. So the red line here is the non-causal control. You can see that everything that is negative means future information, which we don't have, but we could imagine that Guru would know that. The TNC, the truncated non-causal, means, look, I don't have the information, so I'm just going to truncate this here and use what I can use. That's, we managed to show that this is exactly what the wave cancelling approach does. So we have a nice benchmark, and now we know what we are missing in that approach, if we are missing anything. There are cases where this part is just zero, so causal and non-causal control are just the same thing. And then we have when we impose causality. So you can see, like, for large times, it's the exact same solution, but we have these peaks here, which we found are typical of when we impose causality. Is a consequence of the mathematics, but the physical interpretation means that if you have some correlations on these disturbances, so if you plot the autocorrelation on the sensor, it's non-zero. Using the current reading, I can kind of estimate with some uncertainty what's happening in the next second. So I can use that information to kind of use part of this non-causal control now. So the physical interpretation that these things compensate for everything I'm missing there. Part of what I'm missing there. And then what we did next is to do a parametric study, right? So I'm keeping this this sensor, but I want to see how my control performance changes if I use any of those actuators. So I have a total of 10 actuators there. And I have here the energy of the target when there is no control, when I have non-causal control. And non-causal control really doesn't care where the actuator is, because it knows the future. So I can apply do a negative wave here before the original wave is created, because I'm all powerful, basically. But any realistic application cannot do that. If you compare, if the actuator is way downstream of the sensor, then all of the controls are the same: causal, non-causal, truncated, non-causal. They all give basically the same response. Which, if you move, would mean that everything in this kernel is to the right there. So there's no negative part, there's nothing to be compensated. That's quite a trivial case. That's exactly what Sasaki did in his study without knowing that at the time. But what you see is that if you just truncate the non-causal control, as soon as the actuator moves to the left of my sensor, we have a drastic loss of performance. If you use impose causality a priori, we can actually have a sensor that is way extreme than my sensor, and we still quite effective in terms of control. So that already shows us that imposed causality a priori gives us much more freedom in the choice of sensors and actuators. There is a robustness question, which I'm ignoring for now, but doing that has this advantage. Other advantage that I don't show here is that, remember that before, to estimate what is happening there, I only needed to do an adjoint sensor on my sensor, adjoint run on my sensor, and followed by a direct one. So to do this control for any of those actuators, all I had to do was like to have my estimation, which I need 2 linearized runs, and I need to get a transfer function from an actuator to my target, which I can obtain using a disjoint run from my target backwards in time. All of that to say, all of these parametric studies we did using 3 linearized runs and post-processing. So the potential of that to do actuator parametric analysis is, I think, it's just fascinating. We have a whole classification of problems if we restrict the external perturbations to a lower rank approximations. We have just 1 or 2 sources of perturbations. We can do a full parametric of sensors and actuators of the problem. Number, position, shapes, everything, only post-processing data of a few direct and adjoint runs, which I think is great for at least a first exploration of the problem, where we place sensors, what we need to do. And then we can do the same thing using now 3 sensors. So again, full parametric study, doing now a total of 3 times 2, 6 plus 1 direct runs. We have a meso control parametric on the actuator position. With 3 sensors are the solid lines. The previous results are in dashed lines. So it's unsurprising that we get a better result when you have more sensors. What that shows is that if you do the naive approach of just truncating your kernel, works quite well if you have 1 sensor. If you have multiple sensors, things start to deteriorate, even if the actuator is downstream. And the rest is basically the same story. We have a more robustness. We keep the control performance even if we are upstream. And then just to illustrate, again, all the control rows were obtained using just a few adjoints, and we can estimate the flow using causal approaches. When I don't have the triangle, I'm minimizing the energy of the whole field. I have 3 sensors that changes quite significantly the control performance. If I add more actuators, I control more. I mean, it's a whole parametric study we did at the time. And I'm going to jump quickly here. We did the same thing now for the nonlinear case. So we start with a very small external perturbation. Solid lines is the uncontrolled flow. Dashed lines is the controlled one. And you can see that we get up to a perturbation amplitude of 10 to the minus 3, we pretty much get the linear regime at some point with this deteriorate, which is expected. The flow gets nonlinear. What is interesting is that if you compare estimation and control performances, the estimation performance degrades way faster than the control performance, which at first sight was a bit surprising because you cannot estimate how can you control. What figure out what was obvious afterwards. What happens is that only the non-linearities became important after my sensors. So when I had the shear layer, the Kelvin Helmut was developing. So what the control was doing was preventing the nonlinear terms to become important. So that pushed this performance a bit upstream. And now we get some experimental results. So everything we did so far was on numerical environments. What we did here is to, okay, let's try use this approach for real. So the first tentative we did was a control of a common system wave. The configuration the same as we had before. We had some disturbance which was imposed on the layer. We want to measure that using a sensor, using an actuator to cancel this thing to minimize whatever we have on the target. My figure just screwed up. Forget about this. What we have here is the PSD of the uncontrolled flow. For a baseline, what we did, we were using plasma actuators, so we had to turn on the plasma, a steady plasma, because by itself we had a reduction of the perturbations because it was changing a bit the base flow. And then we could compare the performance of the truncated non-causal and of the Wiener-Hopf approach, or causal by construction. And what you see is that here the gain is not huge. We already have some gain, even if the setup was originally designed specifically for the wave cancellation approach. What we did later was a more challenging case. We went to a fully turbulent jet. So this is an experiment we did in Poitiers. Was I forgot to add the reference here, was Meyer that did that in his 2022 paper. where he did two things. So initially he did the same thing as we had for the boundary layer. We had some loudspeakers here which create excitations on the nozzle lip. So axisymmetric excitations, because we're only interested in axisymmetric modes in this experiment. So we want to reinforce that to make it like easier, to be honest. We measured these axisymmetric modes using an array of 6 microphones here, and we're using 6 loudspeakers connected to a small tube that's creating a synthetic jet close to the shear layer, is slightly downstream. And the goal was to control perturbations further downstream, which we were measuring using a hot wire. We did that using this external perturbation, but afterwards we removed that and we did the control of the naturally turbulent jet. This was an easier target, but what we found out is that we can also control the naturally turbulent jet. So that's the only one I'm showing here. We have the uncontrolled flow, which is on black here. It's important to say here that here we chose a specific frequency range to control. So we're not controlling everything. Was in between 0.4 and 0.7, if I remember correctly. And we compare a steady actuation, so we're just blowing the actuators randomly to be sure that any gain we have is not an artifact of just changing the base flow. If you do that, you have this huge peak. So that gives us confidence that we're not screen biasing our results favorably. And then you compare, again, the non-causal control, the truncated non-causal control to the causal control by design, and you have a nice reduction of, we got like 50 or 40% of the turbulent energy out of hot wire we managed to reduce using a linear control on a fully turbulent jet. And we managed to show that this is not even an artifact of the point where we do control. We later moved our hot wire along the x-axis, the jet axis, and we have perturbations that consistently reduce it downstream all the way up to 7 diameters downstream of the jet. So we really managed to change the dynamics of the turbulent jet using a linear control, a bunch of microphones and so I'm going to quickly skip the conclusions. We have a nice method that can use for complex flows. We don't have to reduce the model. When we have like straightforward implementation on experimental data, and numerical tools that do that are fairly expensive, well, other than the linearized and brunt if your system is. So I'm gonna go quickly here. That's my toy model I'm working right now. The question is about flow modeling. So when modeling flows using the linear system, we either use eigenmodes. So we're talking about eigenanalysis, and you look for the modes that creates either the vortex shift, the von Karman vortex shift, or here I'm just showing an eigenmode of a switching jet. We do linear analysis, we get Ig of the matrix A, and we look at the frequencies. Or people do the resultant analysis where I assume that there is external forcing. We look for the forcing that optimally forces the flow, and we got a response. This is now all nice. I'm going to focus on those two cases because I think they illustrate the point that bothers me. In the cylinder wake, we know what happens, right? It's the instability of the wake. We know that the so-called wave maker is located like right behind the cylinder, so we have a pocket of absolute instability, the technology of Schumann and company. But if you just look at the mode, well, this is not an eigenmode, but if you look at an eigenmode, we're going to see that everything is dominated by the downstream region. So if you don't know the physics of the flow, you don't know if this thing is driving that or that thing is driving this, right? So our question is how to identify the active part. For this case, when the resonances are local like that, it's not that complicated. But you know, it's something that demands a study. We have to delve into the physics to get this. For splitting jets, it's slightly different. So we can do the same thing. We can compute an eigenmode. We got an eigenmode like that. I'm showing shortly after the spectrum, and the question is, how can I make sense of that? For me, it looks like a Kelvin-Helmholtz wave, right? The problem is that Kelvin-Helmholtz is typically a convective instability, and for a switching jet, what has an absolute stability. The whole thing is just resonating and being noisy. So either we have some sort of absolute instability, which no one found yet, or there is some sort of long-range mechanism. So this Kelvin-Helmholtz wave travels downstream, it gets reflected at some point, it's going to move upstream, be reflected by the nozzle, creating a resonance mechanism. But how identify that? Many people created models for that. I don't have a full bibliography review, but some people just assume that there is two waves responsible for the feedback, and they create a model. The problem is, what are the reflection coefficients? You have to guess. Well, at the nozzle, you can actually compute them, but downstream, this wave is being reflected by shocks. It's not locally parallel. It's hard. Some other people use a different framework. They assume that the shock cell structure is periodic. They found Nogueira found absolute instability in this flow, which is amazing work. The problem is this is not the answer, because we know that the jet leap plays a role in the switch. If it was some sort of absolute instability downstream, it should depend on the leap. It's a nice study. For me, what it says is that if you have an infinite shock cell, this would resonate by itself. It's just not what we see in the lab. So my question is how to figure out what's going on there. And my core problem to approach this thing is wave reflection. So the idea here is that I have an incident wave. I'm assuming that I have two barriers here of any type that reflect and transmit waves. And the question is, what is my reflected wave? What is my transmitted wave? The idea here being, if I just move to this problem, if I can put a Kelvin-Helmholtz wave here and measure what comes back, and with some hope to understand why it goes back, I can kind of put my pieces together to get a resonance mechanism together. So if you do a global solution of this problem, which is my analogy to the global mode, we end up with an expression, right? This is the total reflection coefficient in terms of transmitted, local transmitted and reflected coefficients, the wave numbers. We have a formula. If you prove it in, it's going to work. It just don't tell me much about the physics unless I really try to analyze the formula. There's another interpretation of the problem, which I like, that you can imagine that this thing is being represented by an incident wave that travels through my domain. Every time you meet the barrier, it is reflected downstream. So there's a gain associated with this step. There's a gain associated with this reflection, and then these reflected waves can suffer secondary reflection. So like basically, this wave here is now reflected at this point and moves to the right. This wave here gets reflected at this point, moves to the left, and it keeps on going, right? If you do those two things, if you add this infinite series, what you get is exactly this thing. But this has the biggest advantage that it's easy to get a physical interpretation of what's going here. We can understand the physical mechanisms. So this is all nice. The problem is that for this simple problem, it's easy to do. I have one wave going to the left, one wave going to the left. How I generalize that? So the first thing we have to do is to know what waves in a general problem are going to the left or to the right. So here I'm doing my core problem is an acoustic channel. So it's the simplest thing we can do. How we identify the wave propagation direction is using Briggs-Best criteria. So all my crosses here are eigenmodes, spatial instability eigenmodes on a plane. And you do Briggs-Best, you increase the imaginary part. When the modes move to the upper half plane, these waves are moving to the right. So when they go to the bottom plane, they move to the left. Thus, I'm marking them with red and blue markers to identify K plus and K minus. So what I want is to get all of the K pluses in one solution and get the secondary reflection using all of the K minus and iterate that. To isolate those waves, Town in 2015, doing his thesis and follow-up works, he did what's called a projection operator that basically filters all of these negative waves, K minus waves, or the total stream propagating waves, to get me only the other ones. So we can do that by brute force, or he has like iterative method to do that. That's beyond this point. There's a numerical method that projects any solution only on the plus subspace. And he uses that to get an approximate solution for a linearized system only by its K plus parts. So he did that for a jet, for instance, and he gets a solution that looks like that. Anyone that did the resultant on a supersonic jet knows that it's basically how the things looks like. He compares this thing to different solutions, and it's pretty accurate because on the jet there is no K minus wave. So by ignoring them, he stabilizes the problem. He can partially match this thing downstream. My toy picture for my model picture for this flow is something like that. I have like one wave he puts on this thing. This wave gets scattered by the by the divergence of the flow into other waves, but all of these waves are moving to the right, so you don't have to care about the left waves. But now I want to get both waves. So how I do that? There's a paper that was published this year. I just have the name of what I want to do is called a Bremer series. But basically the idea is that I'm getting my equation, which I'm marching x, and decomposing into, I'm adding p plus and p minus in front of every k, where k is just my state space. And the idea is that if p plus and p minus expand the whole subspace, which is what I had before, I only had minus or plus waves. This is exactly the same equation as I had before. I can rearrange it into a k plus part and a time k minus part. And the idea is then I'm going to set k minus to 0. I'm going to march only my k plus part. I cannot solve the full equation because I'm ignoring part of it. So there's always some residual on this equation. But then I can later come back, integrate the k minus with my previous k plus. That's going to give me some reflected waves. It's not going to exactly solve the equation, but I can keep iterating. So I keep updating my left right going waves and my left going waves to try to get a solution. So what I do is that those two terms here, I'm discretizing them using a backward differentiation scheme. Here, gear to upwinding to the left, here is downwinding because I'm marching in the other direction, such that those two methods are stable on the direction in which I'm marching. And just to be sure I'm not screwing this up, I'm comparing to I get the solution, I use a centered finite difference scheme just to check that it's not because I got a solution of that I didn't make a mistake here and the solution is not fit. So that's my problem. I had a classical channel flow, acoustic channel. As reflection point, I just added 2 hotspots, and they are on purpose. They are not symmetric here to not bias my solution. So if the reflected waves are going to be what they are, I don't know a priori. And if I do that, what I have here, I start. This is my first k plus Martian, right? So I initialize my flow on the left with a plane wave. This wave is traveling downstream. It reaches the reflection point here. And we see that the wave pattern gets more complex because my temperature profile is not uniform. So here we have second and third harmonics that start to play a role in the flow. It hits the second reflection point. It gets further complexified, but no, all those waves are traveling to the right. I then compute all the residuals of my equations, assuming that this is my solution. I use those residuals to get my k minus wave. So what we see here, the polar scale is a bit misleading, but basically we have 0 throughout here, which is kind of expected. But on the first reflection point, we start to see the formation of downstream traveling waves, which are further amplified when we reach this position, which was my first reflection point. So again, we have first reflection, second reflection. Those two reflections are building up my waves when they travel to the left. I get those 2 waves, which are now my guess for the solution. I compute the residual and I repeat. So here we have the same thing. Now I get the secondary reflections on this point, secondary reflections at this point, which forms a new set of k plus waves. Here again, I have tertiary reflections and it keeps going forward. Right? At some point, the figures start to resemble the same. It's because we have just this resonance in between these 2 reflection points. But if you look at the amplitudes, we have 10 to the minus 3, reaching 10 to the minus 4. So the series is convergent in a way. So here's a messy plot I use to understand if my flow is working or not. Those are all norms. So here are the norms of my K plus solutions. So I basically start up here, and at each iteration, it's still as the norm is getting smaller. So that gives the idea of my solution is converging. Likewise for all of my upstream traveling solutions. And if I compute the residuals, we get roughly the same trend. All the residuals are going to zero. All the plus masses and then all the minus masses. If you do now my final sanity check, this is the residual at each iteration. The blue lines are using the backward difference finite difference schemes, which is the one I used to spatially match. So I would expect this thing to go to zero and it goes to the minus 12. If you keep iterating, it reduces. But what gives me confidence that this works is that if I do a finite difference scheme, like in the first iteration, you say like we have some background residual here. At some point, it follows the residual I'm using in my spatial marshalling. But that tells me is that these waves has important reflections that my centered scheme would, is missing. So it realizes that something is missing in this solution. As I keep iterating, this part which is missing goes down. At some point, I have a background residual because it's not the same numerical scheme, so it's natural that they're not going to both be zero. So that makes me pretty confident. If you summarize this plot, now doing a more parametric analysis, all the solid lines are the residuals of my backward space, my BDF integration scheme. All the dashed lines are marked control using a centered finite difference scheme. I forgot to mention, but for the control, I'm always using a higher order scheme just to be sure that it's closer to the truth. And what I'm doing, I'm increasing the order of my margin, and I'm also changing the spatial step. And look, if I start with order 1, that's my residual when I compare it to the final difference. If I decrease my order, I get smaller residuals, further smaller residuals, which points toward the fact that this thing is convergent, and likewise, if I reduce my dx, the solutions are always convergent. So that's all fine. The missing part for me before going to complex flows was in many flows we have saddle points. Then the question is what I do with a saddle point, because a saddle point is when a k plus and a k minus waves meet, and then I don't know if this thing is plus or minus. I mean, it's both at the same time. How we handle that? And that's where I spend like most of the time with this work, is trying to figure this out, because if I want to do screeches, it's going to have saddle points all around. There's no way around that. What apparently works quite well is I'm relaxing the condition that my projection operators need to add to I. I'm just naively splitting my equation in two, where I'm saying that on my plus wave, I'm keeping all of the downstream propagating waves and what I call P0, so stuff close to the saddle point. And I'm keeping this thing also on my K minus wave. So if I go back here, this is my spectra away from the reflection point, and now I'm increasing the temperature difference to force the formation of a saddle. In the previous solution, there was no saddle. A K plus wave was always a K plus wave. Here, things start to change. And my approach is that, okay, here I can easily cut this domain saying I'm keeping these waves in one solution, that waves in another one. Here what I'm doing is that everything in a circle around here, I'm keeping in both solutions. This creates a problem because the solution, well, a theoretical problem because the solution is not unique. I can add these waves either to here or to there, but it didn't create, then I don't have any formalism for that. But what I did was just to try this out on a flow. It's the same flow, I'm just increasing the temperature difference on the reflection points. Same pictures everywhere. I have way more lines because I did way more iterations to make a point that once you get to the final check here, we don't simply get the background noise, but we have some residual of the reflection points, which I think is somewhat related to this inconsistency between the K plus and the minus. But the good thing is that apparently if you increase the order or the times or the number of points, those things go to zero. So now it took me almost a year to get it right. I think now I have something that confidently marshal complex problems to figure out like pluses and minus wave, get reflection points. And the next step now would be to use the iterative projection operations of town to be able to approach bigger problems. This is quite naive. I have 20 points in the right direction, and use that to really study speech flows and other types of flows. So I think I went over time. I'm sorry about that, but that's pretty much it.
It's okay.
Okay. Thanks for the attention. If anyone has questions, please.